Hello, AP Chem students, and welcome to Unit 5, Kinetics. This is topic 5.1, reaction rates. The learning objective here is 5.1.a, explain the relationship between the rate of a chemical reaction and experimental parameters. So let's jump in. So first of all, let's talk about what kinetics is. So kinetics is the study of rates of chemical reactions, the factors that affect rates, and reaction mechanisms, which is a series of steps by which reactions occur. And so essentially all of kinetics is talking about these three topics. Kinetics determines how fast a reaction proceeds, not if a reaction proceeds. The if a reaction proceeds will be our next unit, which is unit 6, which is thermodynamics. So this graphic, the discussion of thermodynamics here is not important at the moment, but I just kind of wanted to show you that kinetics is this part of the graph here, the beginning part of the reaction where you're starting from a reactants and you're trying to get kind of up and over this energy hump to get to form the product. So this is where the speed of the reaction is really determined. So these are terms that we're going to get into as we move through Unit 5, but this is maybe a graphic you want to come back to. I thought it was really nice for this comparison of what kinetics covers. So the factors impacting reaction rates can vary widely, and they're impacted by several different factors. So first of all, we have the concentration of reactants. And in real life, we see this because increasing concentration of CFCs in the atmosphere is speeding up the degradation of the ozone layer. So as we increase that concentration, the speed of that reaction is increasing. We have temperature, adding sugar to tea when it's hot instead of when it's cold. It dissolves better when it's hot. Surface area, using a sugar packet instead of a sugar cube. And then catalysis. And a great example of catalysis is enzymes in the body, which are used to speed up many biological processes. So then these factors are really nicely summarized in this graphic from compound interest. So the collision theory is something that we're going to get into a little bit later in Unit 5. But this just shows you if we increase the concentration of reactants, we increase the frequency of collisions. And then we see that that means that the greater number of particles are available to react. Okay. If we increase the temperature of a reaction, we increase the frequency of collisions. And we also increase the percent of successful collisions. Here, if we increase surface area, we increase that frequency of collisions again. If we increase the pressure, we're increasing the frequency of collisions. And then a catalyst works in a slightly different way. And we're going to talk about that later. But essentially, what you need to know at this point is that in order for a reaction to occur, you have to have particles collide. They have to collide in the correct orientation and with sufficient energy. But again, we'll come back to that again later in Unit 5. So got a couple of vocabulary terms for you so that you can kind of understand what we're talking about as we move through. The first one is a catalyst. A catalyst is a substance that speeds up a reaction, but is not used up or changed during the reaction. We're going to get much more into catalysis as we move through Unit 5, particularly in the second half of Unit 5. Rate is the amount of change over time. We're going to look more at that in just a second. And reaction rate specifically is the change in concentration of a reactant or a product per unit time. So it looks like this. You have the change in concentration of A at time 2, and you subtract its original concentration or concentration at time 1, and you divide that by the difference in those times. And so this is rate. This is true for any rate. You can talk about a rate of speed of your car, for example. You can talk about a rate of change of inflation. So there's a lot of different rates. But in this situation in chemistry, we're going to use it with concentration. Okay, so as a note, conventionally, we express reaction rates with a positive value. But remember that because reactants are disappearing, those rate expressions, you'll probably see it with a negative sign because that concentration is decreasing versus the products where the concentration is increasing. So rate is not constant, it changes with time, and we can see that with a graph that looks like this. So instead of seeing straight lines, we see curves. So this graph shows the change of concentration with respect to time for the reaction 2N2O5 yields 4NO2 plus O2. So I want to point out a couple of things here. First of all, there's your concentration on your y-axis. Time is on your x-axis. And so then about the lines themselves, you see that we have 4NO2 are produced for every 1 O2, and that matches the stoichiometry in the reaction. We also see that your reactants here decrease as your products increase. Then we see that the lines eventually level off like this. That's when they reach a point called equilibrium, and that is its whole own unit in unit 7. So how do reactions change with time? So over time, the concentrations of the product increases and the concentration of the reactant decreases. Because the reaction rate changes with time, it's customary to determine the instantaneous rate. And this is found by determining the slope of the line tangent to the curve at some time point. And if you are in calculus, that math is something that might sound familiar to you, but you do not need to know or understand calculus in order to do the calculations that we're going to do with kinetics. The stoichiometry of the reaction also contributes to the rate. So this is what the slope of the line, tangent line to the curve looks like. Okay, but again, that's not something you need to worry about. You're going to be able to do this math without doing any kind of advanced calculations. So for now, for the reaction AA plus BB yields CC plus DD, the rate is equal to negative 1 over A, so this is the coefficient. The change in concentration of A over the change in time is equal to negative 1 over B times the change in concentration of B over the change in time is equal to 1 over C. Notice it's positive now. Change in concentration of C over change in time is equal to 1 over D, change in concentration of D over change in time. Okay, so what does that actually mean? If you know how fast A is being consumed, then we know that B is being consumed B times as fast, if you want to think of that. So if your A is 1 and your B here is 3 for your coefficients, if we know the rate of A, we know that B is being used up 3 times as fast. And so that's why you see this coefficient down here next to your time, right? And then if we know the rate at which this is being consumed, we know the rate at which this is being produced. And this is all based on stoichiometry. But again, this is if you already know how your concentration is changing with respect to time. For one of the species, you can figure out how the concentration with respect to time changes for another species. All right, so what should you be able to do with this? So you should be able to write the mathematical formula for the rate of the appearance or disappearance of a species in a chemical reaction as a change in concentration over time, paying attention to your stoichiometric factors, and then evaluate how a change in reaction conditions, i.e. surface area, concentration, or temperature, will impact the rate of reaction. So in other words, if we decrease the surface area, if we increase the surface area by decreasing the size of the particles, it will speed up. If we increase the concentration, it will speed up. If we increase the temperature, that usually makes it speed up, or that does make it speed up, and things like that. Back up here to writing the mathematical formula for the rate of appearance or disappearance, you should also be able to use values that are provided, plug into that equation, and then relate the rate of one species to another species. And that's it. And I will see you soon for topic 5.2, where we'll get into rate laws.